Okay, for what we have in this introductory section and what we have for systems of linear equations, okay, first of all, we have by definition a linear equation is an equation that can be expressed in the form where we have a of 1 x of 1 plus a of 2 x of 2 plus a of 3 x of 3 all the way up to a of n x of n is equal to b. And for what we have for the characteristics of the coefficients as well as the subscripted value n, okay, we have with the coefficients a of 1, a of 2, a of 3, a of n, and also b. Those can be real or complex numbers. And in the case of what we have with the variable n, okay, this will be regarded as a natural number. And just to sort of clarify, now we have with a natural number, this will be the positive integers. Okay, so we have with natural numbers, you have positive integers or the positive counting numbers. So you have 1, 2, 3, 4, 5, 6, and so on. And now, so this is what we have with individual linear equations. Now, carrying over to what we have with systems of linear equations, and we're going to have various types, and one is going to be where we have one solution, and this will be what is regarded as a consistent system. And a consistent system will be a system with one solution, and that can be graphed as a single point. And we have, just for instance, okay, say if you have a two-equation system, and we have the L of 1 is equal to the graph of the first equation, and we'll have that L of 2 is equal to the graph of the second equation. One solution is going to be indicated by intersection at a single point, okay? And say if you have x of 1 and x of 2 respectively at 3 and 2 to be the only values of x of 1 and x of 2 that will work into both equations, well, the graphs of both equations will intersect at that particular location. So a consistent system is going to have one solution. Now, as a bit of an opposite, now we will have what is regarded as an inconsistent system, and this will be a system that has no solution. So there'll be no values whereupon x of 1 and x of 2 will intersect, and the graphing of an inconsistent system will be represented by lines that run parallel. So you have like a graph of the first equation, graph of the second equation, and there's no commonality that exists between x of 1 and x of 2. So we have no intersection, so there is no solution to the system. Okay, we have third case, you have another type of consistent system, and let me specify a little further. Okay, we have another type of consistent system, and this will be an identity. Now, the author mentions that a consistent system will have either one solution or infinitely many solutions, but we'll say for that which has infinitely many solutions, okay, this would be an identity. Okay, and the reason for this is that if you were to graph, okay, you have the graphs of the equations to be identical. Say we have the graph of the first equation, the graph of the second equation, we have an infinite number of points that will intersect. So the lines are identical, thus you have all commonalities between x of 1 and x of 2. All right, now in the crossover to what we have as a sample of a system of equations, and we can express this in the form of a two-equation system. Now, you will be looking for the values of x of 1 and x of 2, where you will have simultaneously that 3 times x of 1 plus 2 times x of 2 is equal to 7, and whereupon we had the sum of x of 1 and x of 2 to be at 3. And now we're going to be looking into matrices. And now if I were to express this system in matrix terms, okay, so for what is regarded as a coefficient matrix, so the first column will consist of the coefficients of the x of 1 terms, so you have 3 and 1. Second column, we have the coefficients of the x of 2 terms, so you have 2 and 1. And we have the third and last column, we have 7 and 3. And those are the values to which we have the respective equations to be set equal. And we're going to be looking into echelon form. And now a reduced echelon form, you have a diagonal array of ones and zeros. And if you notice, you have for the first row, you have 1, 0, alpha, and this would signify that x1 is equal to alpha. Then you have 0, 1, beta, and this would be where you have like 0x01 plus 1 times x2 is equal to beta. So this will signify that x2 is equal to beta. And to show you what the outcome will be for this particular system. Say if I go with the matrix route. So again, we have with the coefficient matrix. So I have 3 and 1, 2 and 1, 7 and 3. And if I put this in terms of reduced echelon form, one pathway is that I can make this 3 into a 1. Or another way I could go about this, is that I can make this 1 in the far left as a 0. But what I'm going to do first, I'm just going to reduce the 3, 2, and 7. So I'm going to take 1/3 of these values. So 1/3 times r of 1. And I'm going to leave the second row untouched. So right now I have 1, 2/3, and 7/3. And I still have 1, 1, and 3. And if I want to make, the bottom row just start out with 0. So what I'm going to do here is that with the second row, I'm going to take away the elements, from the respective positions in the first row. So we have R2 minus R of 1. So I have R1, I have 1, 2/3, 7/3. Now if I take the elements from R1 away from R2, so I have like 1 minus 1, that will be 0. 1 minus 2/3 will leave us with 1/3. And I have 3 minus 7/3. 3 is like 9/3. Take away 7/3, so I have 2/3. Now, and let's say that if I go ahead and convert what I have here. So I'm going to say that I can make this 2/3 into a 0. So we have the way to eliminate 2/3 is to take away 2/3. And with respect to what I have in the second row, I can say that I have R1 minus, since I need to convert this 1/3 into 2/3, I can say that I have R1 minus 2 times the elements in the second row. And right now I have the second row untouched. All right, so I have 1 minus 2 times 0 is still 1. And I have 2/3, and 2 times 1/3 will be 2/3. 2/3 minus 2/3 will be 0. 2 times 2/3 is 4/3. 7/3 minus 4/3. This will leave us with 1. All right, so I had the 1, 0, alpha, where alpha is going to be at 1. And if I get the bottom row to consist of 0, 1, and whatever beta converts to, so what I need to do here is I can take 3 times the second row, Three times 0 is 0. 3 times 1/3 is 1. 3 times 2/3 is going to be at 2. And for what we have in this particular set will be that we have x of 1 is equal to 1. And we have the x of 2 is equal to 2. And that will be our solution in this system. As a second system, we're going to have 3 equations, and we have with the lineup, if I put this in terms of a coefficient matrix, since I do not have specified an x of 1 term, the first row will start out with 0, 1 for x of 2, 4 for x of 3, and -5, and matching the coefficients with respective positions. And now I have 3 rows and 4 columns. And in the solution, okay, we would have a reduced echelon form. So you have, again, 1 0, now another 0, then you have alpha, so this will be in reference to x of 1 equal to alpha. Then you have 0, 1, 0 beta. This one will be in reference to 1 x of 2 is equal to beta. And we have 0, 0, 1 gamma, so this will be in reference to 1 x of 3 is equal to gamma. Now if I take this system of equations, all right, and get it as quickly to reduce echelon form as much as possible, notice that the upper left-hand corner has 0, and you have the first elements in the second row to consist of 1, and I am at liberty to interchange the elements from the first 2 rows. Okay, so interchanging the rows, I have this line up, and if you notice, okay, if I want to line this up where I can make the 3 at the bottom into a 0, okay, so what I'm going to do here is I'm going to take away, okay, 3 times the first row from the third row, and I can write symbolically where we have r of 3 minus 3 times r of 1, and we have in the rewrite, again, the first 2 rows are still intact. Now we got 3 minus 3, so that's going to go to 0. And we got 7 minus 3 times 3, so that will be negative 2. 3 times 5 is 15, taken away from 7, so I have negative 8. And I have negative 6 minus 3 times negative 2, so that will be at 0. And if I continue, okay, so I got 1, 0, 0. And if I make the top and the bottom numbers from the second column at 0, I can perform simultaneous operations. Now I have the 1 in the second row, second column, and what I can do here is I can make this 3 into a 0, so I can say that I have r of 1 minus 3 times r of 2. And also I can say simultaneously go from negative 2 to 0, I'm going to add 2, so I can say that I have r of 3 plus 2 times r of 2. So for what I'm going to get here, okay, so I have 1 minus 3 times 0, so I have 1. 3 minus 3 is 0. 5 minus 12, this will land at negative 7. And we have negative 3 times negative 5 is a positive 15. Negative 2 plus 15, this will come out to what we have in 13. So we have 0, 1, 4, negative 5, and have 0, and you have negative 2 plus 2, that will come out to 0, and you have negative 8 plus 2 times 4, that is 0, and you have 0 plus negative 5 multiplied by 2, so that would be at negative 10. And for what we have in this particular case, all right, turns out that this particular system cannot be reduced. In other words, I cannot make the 4 into a 1 and the negative 7 into a 0 without affecting the other elements. In other words, I can't do it without affecting the 1s and the 0s already formed that would have otherwise led to the reduced echelon form. So we have, in this particular case, all right, so we have can't be reduced. So that means that there is no solution. And that means in consequence that the system is inconsistent.